All right. Hey, y'all, and thanks for stopping by to check out my poster. It's too bad we couldn't be sharing it with you in person because I was very much looking forward to this conference. But at any rate, I'm Ben McDonald. I'm a postdoc in the SWOG group at MIT. And today I'm excited to share with you some of the work that I've got to be a part of using polymers as surfactants in dynamic double emulsions. And so just to quickly introduce emulsions, they are suspensions of one, say, phase inside another phase, usually liquids, um, and these are immiscible liquids. So these suspensions are typically stabilized by surfactants. And we have there countless examples of emulsions in our everyday life, medicines, food like ice cream, mayo, uh, milk, you name it. And um, again, what is the crux of all these endophilic molecules that stabilize the surface, essentially lower the surface energy or the interaction energy between these two phases. And so we use, we create what are called dynamic double emulsions. And so these are double emulsions in that rather than one phase suspended inside of another phase, two phases suspended inside of one phase. And so these two phases typically are also immiscible, and they are hydrocarbon and a fluorocarbon, represented in red, the hydrocarbon, the fluorocarbon. These are in aqueous solutions. And so these are dynamic because we can essentially um, favor or increase the surface area of one causing this one phase where they're causing this encapsulation using surfactant that is interacts preferentially water in one of the two phases. And this is all again based on surface tension. And so you can see that these are indeed dynamic because this is a live video in regular speed. You can see it repeats a few times over the course of this presentation, but by adding a surfactant, it causes this whole scale change in morphology. And in this case, we've added zonal fluorocarbon flavored surfactant that's causing this, what we call the Janus, or these half and half two-phase droplets to switch into this capsule configuration. And so we make these really beautiful monodispersed materials, as we call them, that pack in these hexagonal structures using a microfluidics platform. And so all we do is we take these two constituents and heat them past their critical mixing temperature. So instead of being two phases, they're one. And so again, these two have to be carefully selected to have a fairly low mixing temperature, anywhere 35 degrees C to 60 degrees C, and then you inject them into a continuous phase of surfactant, mixture of surfactants, and then as they cool, they become these nice phase emulsions, colloids. And so what's really interesting about these materials too is that the fluorocarbon, hydrocarbon phases have different refractive indices, right? And so as you may well know, when you have two phases that have two refractive indices, at that interface we have occurs it's called refraction, right? The same way the pencil in a glass of water bends. Bends excuse me, with these interfaces. And so in the simplest sense, this kind of plays out and either in the Janus state, light penetrates through evenly, so we have transparent droplets. Again, this is kind of a zoomed out picture. And then any time we change the focal length of these as lenses, we get opaque materials. But what's even, I think, to me more interesting is the use of what's called total internal reflection which again is a property that arises from refraction. But total internal reflection occurs when light hits, again, that refractive index boundary, but it hits it at such an angle that rather than traveling through and bending, it actually bounces off. And so light, if it's, say, emitted by a fluorescent dye that's localized in this hydrocarbon layer, a certain percentage of that light will hit at that angle and basically bounce upwards and out of the droplet. And so if we're monitoring the emission of light 90 degrees, basically from the surface, normal to the surface, as this droplet kind of functioning as an aperture changes configuration, we can basically see a very, well, we see a difference in the observed emission intensity. It creates a very sensitive sensor if we're able to basically then now tie in the surface energy to programming surfactants, and surfactants that are programmed to respond to an analyte choice. In our case, this is typically, say, pathogenic bacteria like Listeria or E. coli, or say other biomolecules or proteins of interest. So again, we're always interested in making sensors. And so we'll return to this, but I just kind of want to briefly whisk you through the different ways that we can use polymers to, again, get these kind of sensing schemes and for loading, again, of these reactive surfactants. And so one of the things that we've recently done is replace the hydrocarbon phase in the droplets with liquid crystals. And liquid crystals, right, differ from isotropic mixtures in that they are fluids with an internal order, and can be seen in polarized microscopy. Right? And so what we do is we actually first have to stabilize, actually, in this case, the internal interface, right, between the liquid crystal and the fluorocarbon, because they actually have a much higher surface energy than fluorocarbon. So we have an internal surfactant, which can be a small molecule or polymer. And then additionally, what where polymers are particularly useful are loading in cargo. And so we have, in this case, a diblock polymer that aligns itself in the crystal phase. But then we have this hydrophilic block that also has this boric acid unit that is able to undergo dynamic chemistry diol. Right? So particularly this is used for sugar. So if you have a sugar conjugated protein, we can stick that to the surface. And then we can use actually the ordering of the liquid crystals to move this carbon around. And so in the pneumatic case, where we have this kind of radial alignment, wherein we have, then at this defect point, we have all of our carbon there, and then by changing, say, the crystal configuration, by modulating temperature, we can actually see here, we can watch a fluorescent tag protein move around the surface. And again, you can also see this in the SMEC, which can be, we can use temperature to move it to the SMEC thematic isotropic. Again, see the fluorescent around. And so one of the other things we've been particularly interested in using polymers is phase selectors. And this is a case where they can do things that small molecules surfactants certainly cannot. And that's because we can basically take small molecules that might say have a preference for water phase or fluid phase, in this case, it's a hydrocarbon phase, and we can string them together. And so we wanted to use these actually to then get to the fourth interface. So I told you about the first three, which was the hydrocarbon nucleus, fluorocarbon nucleus, and that internal, in this case, the hydrocarbon, fluorocarbon. But additionally, there's a line on the extent at the outside of the droplet where all three phases meet, and we call that the three-phase line. And so we are particularly interested in what will happen if we localize carbon. In this case, we're interested in depositing gold and making gold rings. And so in doing this, the simplest way to realize this type of polymer is just an PVC to polymer. And then if you're ignoring the chain end, which in this case, for this being about 35 molecule, right, a phenyl group and two proton groups don't really make any difference. So when we disregard those, there's only really 3 linear combinations, and here they're just kind of named for whatever the center block is. And we didn't know, a priori, if these would function differently in surfactants. And so we made all 3 of these and then put them into droplets. And interestingly, you can see that they actually do function differently surfactants. And basically, you can see here, this is just a graphic chart showing for a certain concentration, the weight percentage of polymer, how does it affect the configuration. So the stronger surfactants, the smaller the sample. And so you can see that they are different. And interestingly, actually, only this water-centered triblockyl polymer lets us have, again, these dynamic double emulsions. So we moved forward with that material. And we added in this reactive ester group, right, that is basically does not react with water, but reacts very quickly with amines. And so this is typically a choice for bioconjugation. We used it with these pegamine from transglobin particles, right? So we have these amines on the surface that will basically conjugate our globin to the surface of the droplet. And then we can perform this electrode scroll deposition reaction to grow these nanoparticles. We were particularly surprised to see that upon this gold deposition step, we see a strong color reflected under the microscope. And you can also faintly see this color if you just shine a strong light on the material. And so what's further just utterly fascinating is that this color is dependent on the configuration of the droplet. And so you can see here, we're actually increasing the size of the hydrocarbon. And what's happening is that we're actually increasing, right, the length of this interface. And so it turns out that this phenomena falls under actually a very recently reported structural phenomena that occurs in concave interface. And that was actually reported by a former group member of ours who is now and this was reported very recently, just over a year ago in January 2019. And so what we learned is that actually our gold nanoparticles are actually scattering light into this and basically enhancing or serving as amplifiers of this structural color phenomena, which basically arises from essentially all structural colors due from light traveling different being reflected and traveling in different distances and then re-interacting with itself and there being resulting interference between these rays. And so you essentially, depending on the wavelength of light, these rays either add together and might coherently interfere or cancel each other out and destructively interfere. And since there's a wavelength dependence on these two different constructive or destructive influences, we get certain wavelengths favored with that. And so what it turns out that the nanoparticles are doing, as I said, they're scattering light, in that there's actually a size dependence in the scattering that we see because actually gold nanoparticles scatter light more strongly with the larger light. But interestingly, as we model this and we kind of interface to 2 computational models of light scattering around gold, off of gold, and additionally the emission of light at the interfaces, we can see that actually the strength of scattering actually competes with the angle of scattering. Because gold nanoparticles actually, as they get larger in size, they scatter light at a narrower angle. And so that's why we see this, we have this kind of computed chart here where we see initially a very strong rise in the strength of gold scattering intensity, or light scattering intensity, that actually decreases as the gold nanoparticles grow and then increases slowly. And again, this is a product that these two competing in. So and finally, I just want to briefly touch upon some of the work that is ongoing and very much in the nascent stages, and that's using living polymers, essentially macroinitiators, as a living surfactant. Right? So what we want to do is take a polymer, align it at the surface, and then use that to grow more polymer from the continuous state, so that we might push our droplets around. And so our macroinitiators essentially have this hydrochloric anchor and they would be hydrocarbon. And then we can basically add in different amounts of this hydrochloric group to tune the surface activity, or basically the part, then how much control how this partitions between being really clean and having it being at the surface for kind of hydrocarbon. And so having this kind of control will allow us to essentially say, for example, extend the lifetime of the ruthenium. That's right. The ruthenium lifetimes tend to degrade in water, so we can kind of keep them nestled and kind of slowly point themselves out at the aqueous phase. And then as they capture the monomers in the aqueous phase, they will stay there as the polymer just grow. Thanks for kind of going on this journey with me through these very different types of ways that we use polymers at the interface of colloid science. And so this work has been funded through a number of different mechanisms from the DoD and itself, and then I personally have been funded through the MIT Visiting Professors and Scholars Program. And to any faculty that are potentially interested in, or postdocs that are interested in participating in this, please again reach out to me via email. Also, if you have any follow-up questions on this work, I'd be very happy to discuss. So, please feel free to reach out. Thanks. Bye-bye.